This is a short video to help you figure out how to do today's work. I'm sorry that I'm not with you all, um, but you can still make progress with our current project. If you do look back at the class calendar for today, there are some specific instructions on what we're going to be doing, and our main goal is to focus on making progress with our simulation about waves on strings in order to make connections between this simulation and what we're going to see and what we have seen in the microwave. So you want to start out by opening this document, the simulation lab handout, either in Schoology or on paper, whichever is easier for you. And the simulation looks like this. By the way, if you do want to look at this class calendar, you can always do that by going to this bit.ly and scrolling down to today's date or any other date that you're looking for. So most of the handout is about focusing on the research questions with an independent variable and a dependent variable. So part A is the same for everybody, and the research question is, how do amplitude and frequency affect energy transfer through the wave? This research question is written in the following form, so you can tell that these are two examples of independent variables, and then the dependent variable is this value for both independent variables that we're going to investigate. So this first question should be really straightforward. You can say that the dependent variable is energy transfer, and then we need to think, what can you measure, observe that will give you evidence related to this variable? We said two things are related to energy transfer here. We can see the particles moving, so the motion of the red or green particles gives us evidence of energy transfer, and also the lines between the particles represent the electric field that is kind of like stretching as they get closer or farther apart. So you can tell if I increase the frequency, the stretching gets bigger. That is, if I pause this, we can see there's a much longer electric field stretch here compared to here, like I was looking at before. And that longer stretch gives us evidence of more energy being transferred. So I've already given you some clues on how to answer this first question. If you want to pause the video and answer this question now, that is a really smart thing to do so that you don't have to come back and answer it later. Next, you're going to see a few of these tables that are asking you to set up your data table and then run your experiment. And I just want to show you what we mean by controlled and independent variables. Keep in mind that anytime you are doing an investigation between an independent variable and a dependent variable, anything that isn't those two variables needs to be controlled, meaning it needs to be held constant. And in a data table like this, we usually like to leave space for you to identify what those actual constant values are in order to recreate the experiment later. So, for example, if I wanted to investigate the amplitude first as my independent variable, I could write amplitude here, and then I would know that the frequency would have to be a controlled variable because I can only choose one variable as my independent variable. A few other things that I would want to keep constant are the damping and the tension. Other things that I could change in this simulation, but I'm not going to change them. So I'll write them down here. Damping and tension are all examples of controlled variables because I'm trying to change the amplitude. Down here, I want to actually give specific values for the independent variable and for controlled variables. So for example, if I was keeping the frequency constant, I would want to write down the value that I'm keeping constant. Let's record the values of all three of these things. I'm going to change the tension to high, and the damping is going to be none, and the frequency is going to be 0.65 Hz. So I'll write F equals 0.65 Hz, damping equals none, and tension equals high. Notice these two squares are blocked out because I'm not going to use them again. I'm going to keep these three values exactly the same. But for the amplitude, I'm going to have to change them for at least three values. So for example, maybe my first value is just what you see here, 1.13 centimeters. And then I would want to write down some notes on the dependent variable evidence, the energy transfer evidence, related to the speed of the particles and the stretch of the lines between the dots. If I really wanted to, I could even pause and try to measure this, but it's less important to measure a specific value for how far they're stretching or how fast they're going than it is to actually write down some notes. So for example, I could say particles moving but not too fast, really small stretch between particles, for example. And then I would change the amplitude by either increasing it or decreasing it, and then go from there. This is going to help you for question 3. And then when we get down to part B, you have a choice. You can either do the regular research question, which is question 6, which is about this quantity called wavelength, which we're defining here. Or if you would prefer to take on something a little bit more challenging, you can skip to question H6, which is about, instead of wavelength, you're going to be studying wave speed. Keep in mind that the thing that makes this a little bit more difficult is that you're going to need to make some measurement and calculation. And we are given one example of how to calculate this here, but the table looks a little different because you're going to measure two values and then calculate a speed from those values. Keep in mind, the wave speed here is not the same as the particle speed. So I'm going to put this on normal, and you can tell we've already talked about how fast are the particles moving up and down. By wave speed, what we mean is how fast is this peak moving from left to right. So in the example, it says the peak of a certain wave moves a distance of 7 centimeters from the piston to the window. That's what it's talking about here. So we're saying, okay, it takes a certain amount of time for the wave to move. And we're not talking about the particles moving up and down. We're talking about the actual wave peak moving from left to right. The simulation has a stopwatch inside it, and you can actually use this stopwatch on slow motion. The stopwatch will run slow motion along with the simulation itself, which makes it easier to make careful measurements. Again, you do not have to do both part B's. You don't have to do the wavelength and the wave speed. You should choose one. And last thing, I don't usually do this, but I'm doing this because I'm not in the room with you all. This is going to go into the grade book, but you may submit one copy for you and a partner. So if you want to work with somebody else, make sure you put your name and their name at the top, even if it's in Schoology. And I'm going to leave it up to you guys to share the work or talk through the questions together so that you're both getting as much out of this assignment as you can.